Seventh graders, today we get to move on to some of my favorite geometry stuff. We get to talk about circles. Have you ever heard of a circle? Of course you have, right? If I asked you to define a circle, how would you do that? And sometimes a circle is so basic and something we've talked about and classified and recognized since we were a toddler that sometimes when somebody asks you, what is a circle? It's a little bit hard to explain because it's so innate in us. So we want to say things like, well, it's a round shape. Sure, but I can make it a lot more mathematical for you. Of course I can, right? Imagine for just a second that you were going to play a game. And I don't know, let's say you're going to play it in Miss McGowan's classroom. We're never going to play this game in my classroom. But let's say there were no desks in the room and I had all the students get up and stand along this wall here from end to end. Everybody's standing along the wall. And I place a ball in the center of the room and I'm going to blow a whistle and I say, first person to the ball wins. If you're all standing up along the wall, is that a fair game? And when I ask that question to a class, everybody says, no, of course not, Miss McGowan, because some people are farther away from the ball than others. Whoever is in the middle of that wall has an advantage, right? So then the next question is, how do we make it a fair game? And the answer is, of course, the same way we make it a truly mad game, mad as in crazy, is we place the ball and have everybody stand in a circle around the ball so that the ball becomes the center of the circle. Because truly what a circle is, you ready for this? A circle is a figure where every point on the figure is equidistant from a fixed center point. Did I just dial up the mathiness there or what? I'll say that again. A circle is a figure where every point on the figure is equidistant from a fixed center point. Imagine the ball being the center point and the students standing around it creating the circle. The whole idea there, though, is that keyword equidistant, which is a fancy word, but it's exactly what it sounds like. It's equal distances or same distances. So with that in mind, grab some pens. You'll want some different colors here and page 71, and let's learn about circles. First, let's make sure we have some of the vocabulary of circles down because we're going to use this vocabulary a lot. So you want to know what I'm talking about when I say it. Okay, so first of all, there is, and I'm going to color code this, there is, as I mentioned, there is a center to a circle. So this point right here, I'm going to draw an arrow to it. And I'm going to say that is the center. And the center of the circle is that point, that fixed point. Sometimes they mark it in a circle, sometimes they don't, but it is the fixed point that every other point on the circle is equidistant from, creating the circle. Okay, so you have to have some kind of center point in order to even have a circle. Now I'm going to change colors and I'm going to write another word that you have probably heard before. That word is radius, R-A-D-I-U-S. Radius goes from the center of the circle out to the edge, and we label it with a lowercase r. I could have drawn that line anywhere. That's a radius. I'll draw one more. This, maybe this way, is also r, because every radii, that's plural for radius, every radius, all radii in a circle are the same size. That's why you guys tell me that's how you make it fair, is because in that case, if we have people standing along the circle and the center is the ball, if every single one of those radius distances is the same, that's what makes it a circle. Every radius in the entire circle is the same, which actually means there's really only that one measurement going around everywhere. Now, the other thing that we can do, and I'm going to change colors again, I'm going to use orange here, is instead of just going from the center to the edge and getting the radius, we can also get something called the diameter. The diameter is like a radius, except for it goes from one side through the center all the way to the other side. So where a radius only goes from the center point out to the edge, diameter goes from one edge to the other edge, but it has to pass through the center. If I drew another orange line that went from edge to edge but did not pass through the center, that is not the diameter. That's something else that you'll learn about in 10th grade, okay? But it's not the diameter. The diameter has to go through the center point. And we use a lowercase d for diameter. So radius is that halfway mark from center to the edge, and diameter is all the way, but really it's just 2 radii, right? It's the radius twice, okay? So diameter, I'm gonna put this, diameter is really 2r, because it's just double that. All right, and one more thing we need to put on here, and I'm gonna use green for this. We also need to be familiar with something called the circumference. Circumference. Oh, that's a big fancy word and it's fun because it's lots of syllables. Circumference. Go ahead and say it. Circumference. What is the circumference? Well, the circumference is like the perimeter of the circle. We don't use the word perimeter because perimeter is for when you have a concrete number of sides. When you're like, okay, I have 5 sides, let's add them together, okay? And a circle technically doesn't have sides because it doesn't have any vertices. It doesn't have any points where sides come together. And this is all stuff we'll clarify as we move forward. But if a circle doesn't have sides, it can't really have a perimeter because it's not a polygon. I know I'm throwing out so many great geometry words right now, but a circle gets its own word, circumference. And what is circumference? Well, if I start at any point on this outside edge of circle and I follow it all the way around, I'm tracing it in green. This distance all the way around is called circumference, and we use a capital C for circumference. So it's really like if I stood in one spot and walked all the way around a circle, that distance that I traveled walking around the circle is the circumference of the circle. All right, now what we need to do, and normally I would measure these items actually in class, but for those of you at home here watching this and working on this, or if you're doing it in class, I have actually pre-measured some circular items. I took my tape measure and I measured it. So I'm going to tell you what those items are. And then just so that you can picture it. For example, the first item that I have measured is one of the circular fans from my classroom. If you've been in my classroom, you know that I have these. Here, I'll show you one right here. You guys know that I have these fans to keep the air circulating. Not only because I don't have windows, but especially during COVID times, we're keeping the air circulating, right? So I have a few of these fans. Notice that they are circular. So what I measured on these items, so the first item was the fan. And when I tell you these measurements, first I measured the circumference, which was a little tricky. And I actually used my daughters to help me because it's hard to hold the measuring tape all the way around. But what that means is I put the measuring tape here and I use some of that flexible, like the ones that seamstresses use, right? And I held it here and I measured all the way around. And I'll tell you what I got for that in just a second. Measured the best I could. Humans, when we measure things, there's often a tiny bit of error, but I measured the circumference. And then I also measured, see on my paper here, I measured the diameter as well. See that orange line diameter? So what that means is I also measured across this way from one end to the other end. And I kind of tried to just measure across as best I can, but I had to make sure I went through the center point. Otherwise, I wasn't really getting the diameter. So I measured the circumference and I measured the diameter. And I did that for the circular fan. And I also did that for the trash can that's in my classroom. It has a big circle opening. So I measured that. I did the trash can. And then I also have a mug in my room. I'll show it to you. Right here. It says daily method. That's where I exercise. So I have this mug here and it has a circular top on it. So I measured the circumference and the diameter of this mug, just the circle on the top, because obviously it changes as it goes through. So that'd be tricky, right? So I measured the circle on the top and I am going to share those measurements with you, but let me just show you one more time before I share you those measurements. I measured circumference, distance around, and I measured diameter, distance across. And I did those measurements in centimeters because I, in general, think that centimeters are a little bit more, they're a little bit more accurate. And also, everybody else in the whole world uses centimeters because their metric system makes a little more sense. Anyway, so I measured everything in centimeters and I'm going to share those measurements with you right about now. And there we are, measurements. Okay, so hopefully it makes sense to you that the trash can, if you've seen the trash can in my room, it's a bigger circle on the top. So the trash can has the largest circumference and the largest diameter. The fan was next with 66 centimeter circumference. That's around the fan, and about 21 centimeter diameter. That's across the fan. And then the mug, of course, was the smallest. So that was 23.6 circumference around the top of the mug and 7.5 centimeter diameter. See, and this one, diameter is easier to measure with an actual ruler across. For the circumference, I had to use a bendy one. Okay, here is what you're going to do now. So I measured the circumference for you. I measured the diameter for you. In this final column here, you are supposed to figure out a ratio of circumference to diameter. Ratio is a fraction, right? So I want you all, go ahead right now, go ahead and pause the video, and I want you to type in a calculator. You can open up Desmos, you can use your calculator, and I want you to type in for the fan, 66 divided by 21. It's a ratio. Go ahead and type it in and get a decimal and write down a decimal, round it to the nearest hundredth for me. That's 2 decimal places. Pause me right now, find that ratio, decimal to the nearest hundredth for the fan, divide circumference by diameter for the trash can, and then divide circumference by diameter for the mug and get this column filled in. Go ahead, pause me and try that. Here's what I got when I typed them in, rounded to the nearest hundredth. 66 divided by 21, 132. And this one was, it was 3.14 and then a whole bunch of sixes, so I rounded it up to 3.15. Do these numbers look familiar to you? And that's what it's asking right here. What do you notice in the table above? This is a value that I'm quite certain you worked with in elementary, and you worked with it in this form, actually. If that doesn't ring a bell to you, what you should see here is that when you took the circumference, and these were just actual measurements that I measured on these 3 real-life circular items. When you took these measurements and did circumference divided by diameter, you got approximately 3.14, which in the mathematical world, some of you in class would be like, I know that number, that's pi, Miss McGowan. And pi is a Greek letter that we use to represent this right here. Throughout history, people discovered that when they started measuring circles, circles exist in nature, and circles kind of blew people's minds because they're very difficult to draw. Nature can make them, but we have a hard time making them without a circumference or without a compass tool, without computers and programming to help us. Circles are very difficult to draw freehand accurately. So people noticed when they started measuring these things, just like I did, when they started measuring the circumference and the diameter, it didn't matter if the circle was really big, like the trash can, or medium size, like the fan, or pretty small, like this, or really, really small, like a tube of lipstick. It didn't matter how big the circle was. Every time they took the circumference and divided it by the diameter, they got this value, 3.14. But it was never quite exact. For a long time, mathematicians thought the circumference to diameter ratio was 22/7 because they really wanted it to be a fraction, a nice rational value that can be written as a fraction. And that was really close, 3.142857. But as our computers and our calculators got better, we realized that that wasn't exactly right. And they are still now today discovering the next numbers of pi, because pi never ends. And because the number pi, look, my calculator has this button pi right here. See that? When I type pi, it's 3.141592654, but those are the only first 1, 2, 3, 4, 5, 6, 7, 8, 9 values in pi. Your calculator just runs out of room, so it stops showing you, but this number doesn't end. And because this circumference to diameter ratio never ever ends, and we can't actually write it, we put a symbol to it. And since the Greeks were the first one to discover this, they chose the symbol. And so the symbol is the Greek letter pi. It is a Greek letter, but in mathematics, it represents a number. It's a constant value. It's this number. But this is way easier to write than this. So we write this. But this is why pi exists. This number exists 4 circles. So it's only going to be used if circles are involved. And this also leads us to something else really important. We can use our math skills from this year and say, well, what if I don't want to know what the ratio equals? What if I don't want to know what pi equals? What if I want to use this to find the circumference? Well, if I times this side by d, because that's the opposite of dividing by d, and whatever I do to one side, I have to do to the other side, that leads me to a nice, handy formula that we are going to use a lot in this class. I showed you where it came from, and now you just get the benefit of using it. So circumference is always equal to the diameter of the circle times pi. So truly, if you want to know the circumference of a circle, all you have to do is measure the diameter. All I really have to do is measure that this diameter was 7.5, and then I could go 7.5 times pi. Watch this, 7.5 times pi. And I should get this approximate circumference. It might be a little off because I was measuring it, and humans measure things incorrectly sometimes. But look at that, it's awfully close, 23.6, 23.56. So we are going to use this formula a lot in class. And we are going to use another formula that I'm going to help you develop. And this is a little bit tricky without the materials and supplies we normally have in class. But we're going to go for it. So I have right here a circle. It's a green circle. Here is what I'm going to do with this circle. Okay. And if you're in class with me, you can grab one of my circles and try this. You can actually do this with any size circle. Draw a circle on paper, cut it out. Or you can just watch, but then you'll have to sketch what I have. Okay, so the first thing I'm going to do with this circle is I'm going to fold it. I'm going to take my green circle, fold it in half. Then I'm going to fold it in half again. So now I have this quarter shape here. And then I'm going to fold it in half again. Gets a little trickier every time I fold. Okay. And then I'm going to fold it in half one more time so that I get down to this size. Now, couldn't I continue folding this? Just imagine. Now, okay, I say couldn't I? Like physically it would get more and more difficult, but you can imagine I could fold this in half again and again and again and again. And technically, if I could fold it in half enough times, I could get these to where they're almost flat, right? So I'm not going to do that. I'm going to stop right here. And then what I'm going to do is I'm going to open this back up and I'm going to, okay, so I have all these folds in here and I'm going to cut it into all of its little wedges. In fact, if you folded it the right amount of times, you would get 16 wedges. Now, you could imagine I could take all of these and I could actually cut them all in half again and get 32 wedges, and I could cut them all in half again and get 64 wedges. This 16 will be enough. Okay, here's the thing I want to make sure we understand though. I didn't actually get rid of any of the circle. The entire green circle is here. I just cut it into pieces. Okay, and the last thing I'm going to do is I'm going to rearrange these pieces and put them onto this blank space of my notes right here. Let me show you how I'm going to rearrange all of those pieces like this. Okay, this is crazy. What did Ms. McGowan just do and why? So I took all 16 of those pieces. This is the entire circle here. So the first thing I want you to understand is that the area of the circle still exists right here on the paper. I've just rearranged the pieces. So I'm going to say a sentence to you and then we're going to come back to this tomorrow. I'm going to say it a couple times. Whatever the area of this green shape is, it's the same as the area of the circle. Okay, I'm going to say that again. Whatever the area of this green shape is, that's going to be the same area as the circle because I didn't actually take any of the pieces out. I just rearranged them. I took each of the wedges up and down, up and down, up and down, up and down. And if you didn't cut it out or find a piece or make a circle like this, if you didn't actually physically do it, you can sketch this figure on your paper and you can kind of show yourself that it's the wedges up and down as best you can. They're little triangles almost. And tomorrow we're going to talk about what shape did I turn it into and how do we find the area of that and how does that lead us to another formula that we're going to use. So hang on to that thought for tomorrow. Try your Canvas quiz. As always, ask me if you have any questions.